Now that we've found the fixed points, let's look at the stability at each of the two fixed points. So first, let's look at the stability at the origin. So what we do, as usual, is we linearize the equations about the fixed point and look at the eigenvalues of the linearized transformation. So to linearize the equations, we would write, for example, x is equal to x star plus epsilon x, and similarly for y and z. And then we plug them into the differential equations, and then we get the linearized equations of motion epsilon x dot is equal to sigma epsilon y minus epsilon x. Epsilon y dot is equal to r epsilon x minus epsilon y, and epsilon z dot is equal to b epsilon z. Or if we want to write this in matrix form, we have epsilon vector dot is equal to the matrix minus sigma 0 r minus 1 0 0 0 b multiplying vector epsilon. So the eigenvalues of this matrix are easy to calculate, and so let me just write them down. Minus b. And then there's two other eigenvalues that are 1/2 times minus 1 plus sigma plus or minus the square root of 1 plus sigma squared minus 4 sigma 1 minus r. So there's two cases that emerge from these set of eigenvalues. One is when r is less than 1. When r is less than 1, then you can see that inside the square root, the 1 minus sigma squared term, there's a subtraction away. There's a subtraction to this term, and so the thing inside the square root is smaller than the minus 1 plus sigma in front. And what it means is that all three eigenvalues are less than 0. So that means that the point 0, 0, 0, the origin, is locally stable. That is, that if I start close enough to the fixed point that I can do a linearized stability analysis, that any point that's close to the fixed point is attracted to 0. But in fact, there's more than that. It turns out that 0, 0, 0 is also globally stable. And what that means is when r is less than 1, it doesn't matter where you start, you'll always end up at the fixed point at the origin. And the way to show this is by constructing something known as a Lyapunov function, which is an energy-like function that always decreases and is equal to 0 at the fixed point at the origin. And this will imply that no matter where you start, you end up at the origin. It's a very beautiful trick that's worth pursuing. So once again, when we're dealing with nonlinear systems, especially in 3 dimensions and higher, one has to develop extemporaneous analysis methods that are suitable for the system at hand. And the Lyapunov function is just exactly that. So the Lyapunov function is some kind of a nonlinear function, and it's typically quadratic in the coordinates, and so it kind of looks like an energy. It has the following two properties. This Lyapunov function h at the fixed point is equal to a minimum. And furthermore, the time derivative of h not at the fixed point is less than 0. So what this means is that if I pick some coordinate that's somewhere in the state space, I have found this Lyapunov function, then what it says is that this Lyapunov function necessarily decays to the minimum point at the fixed point, and so no matter where you start, if you find this Lyapunov function, you are forced by this flow to go to the fixed point. And so it means that every point, no matter where you start, ends up at the fixed point. So let's try and invent this Lyapunov function for the Lorenz map. And it turns out that the appropriate Lyapunov function is it's quite simple, a quadratic function that kind of looks like a potential energy, x squared over sigma plus y squared plus z squared. So this certainly has the property that when x equals y equals 0, it's a minimum of the function. And as we're going to show now, the time derivative of this function is always negative except at the fixed point. So let's compute h dot, and to avoid annoying factors of 2 everywhere, let's multiply through by 1/2. And then this becomes x dot over sigma plus y dot plus z dot. And then substituting x dot, y dot, z dot into this equation and just doing some very simple, I'm going to skip one step here. What one finds is that this is equal to minus x squared minus y squared minus bz squared plus xy times r plus 1. And we can make this obviously be negative everywhere by completing the square of the first two terms and writing this as minus x minus y squared. And so to make this a complete square, there's a factor 2xy that we've inserted in here, And so we have to take away a factor minus 2xy. So we get minus bz squared plus xy r minus 1. And this is less than 0 for r less than 1. So we've successfully constructed this Lyapunov function, which is a minimum at the fixed point. The flow of the Lyapunov function is always negative. So if we start somewhere in the state space, then the Lyapunov function necessarily forces us to end up at the fixed point at the origin. So in fact, the origin is globally stable. Okay, so what happens when r is bigger than 1? So when r is bigger than 1, then this second factor is now a positive correction to the 1 plus sigma squared. And so it means that there will be now, of the 3 eigenvalues, there will be 2 of them that are negative and 1 that are positive. So in this case, just to summarize, we have 2 eigenvalues which are less than 0 and 1 eigenvalue which is greater than 0. So this gives us a saddle point. If we look at the value of the fixed point value as a function of r, so let's plot x star as a function of r, then what we have is a supercritical bifurcation that we've seen before in our study of two-dimensional systems. Until r equals 1, the fixed point at the origin is stable, and then it becomes unstable, at least in one of its coordinate directions, and so they'll represent that by a dashed line. And we have 2 symmetrically located fixed points at plus r star or minus r star. So this happens at a supercritical pitchfork bifurcation, and the bifurcation point happens at r equals 1. And so this is the stability of the fixed point at the origin.